Welcome learners. I am Dr. Pawan Kumar, Assistant Professor in the School of Sciences, IGNOU. So today in this talk we are going to discuss BFS algorithm and its applications. So in this session our aim is to just describe what this algorithm is and look at two specific applications of this algorithm. So before we go into the session, let me just tell you what are the things that you need to know to understand this session fully. So you must know what is a graph and some basic concepts of graph theory like walks, paths, cycles, what is connected graph, what are components of a graph, eh, and of course what do we mean by a spanning tree. The BFS algorithm, which is an abbreviation of breadth first search algorithm. So it is mainly used to construct a breadth first search to construct a spanning tree in the given graph. Of course, the graph must be connected because if the graph is disconnected, then it does not have any spanning tree. So let us start with just first introduction of what we mean by BFS algorithm. So it is a graph traversal algorithm. Traversal algorithms generally just traverse the vertices of the graph that is given as input in a certain way, in such a way that when we visit a vertex v from current vertex u, then that visit only takes place if there is a direct edge from u to v. This can be just thought of just like suppose you are traveling in a city, so you just traverse from one point to another using some road, right? So let me just take some real life situation before coming to the actual algorithm. You are given a network of cities where cities just where the nodes represent the cities and two cities are connected by roads. So edges represent just the roads, and you have to suppose you are standing at some point and you want to deliver certain packets to each of the cities in the network. So you would like to do it as fast as possible. So this can be done provided you know the shortest paths from each vertex to every other vertex. So this is what exactly application where such kind of graph traversal algorithms are used, and this BFS algorithm is just one of the fundamental algorithms. There are other algorithms like depth first search or many other algorithms like Kruskal's algorithm and Prim's algorithm. They are also used in some way to construct a spanning trees and traverse graph. But this is the very fundamental algorithm, and let us see now what this algorithm is all about. So just look at the graph given to you. On the left hand side you have one graph, and on the right hand side it is a spanning tree of this graph. So this is just one spanning tree in this graph. Of course there could be many other. For instance, just look at the tree formed by the path 1, 2, 3, 4, 5, 6. So that is also a spanning tree. But here we are not going to enumerate all the spanning trees. Instead, our focus is to construct one spanning tree algorithmically. So now the algorithm requires mainly two containers, say T and Q, where T stores the edges of the spanning tree and Q is a Q data structure which stores the vertices as they are widgeted. So in data structure you must have studied the concept of stacks and queues. Stacks works on the principle of last in first out, whereas queues work on the principle of first in first out. So in queue, when we just visit vertices, we just insert them at the end, and vertices are removed from the front. First in first out, FIFO principle. So now let's look at what the algorithm is. So the algorithm is given here. It needs a connected graph G with the root vertex R as input. Root vertex is just a vertex from where you would like to explore the graph, from where you would like to traverse the graph. And the result is just a spanning tree of G rooted at R. In practice, the graph need not be connected, but because we have designed this algorithm to find the spanning trees, and we know that connected graph, a tree is spanning if and only if the graph is connected. So disconnected graph do not have spanning trees. So therefore we assume that the graph should be connected at this point. Later we shall see how to deal with general graphs. So we are given a connected graph G as the input with the root vertex R, and the result will be a spanning tree of G rooted at R. Actually T just stores the edges of the spanning tree that we are going to construct. So now there are some initialization steps, and then there is a main loop. So initialization steps is just as follows. Just mark R as visited and all the other vertices as unvisited. So that means the root is initially marked as visited and every other vertex is marked as unvisited. And the T contains nothing here, it is empty, and the Q contains just the root vertex R. So this is initialization step, and then the main loop starts. So the main loop is as follows. While Q is not empty, do certain things. What are these things? Pick the first vertex, say U, from Q, and then for each V belongs to NGU, do again certain things. So that means for each V belongs to NGU means for each neighbor V of U. NGU is just the set of all neighbors of U in the graph G. So for each neighbor of U, we just check whether that neighbor is unvisited or not. If it is visited, that means we do nothing, but if it is unvisited, then we have to perform certain steps, and these steps are: append the edge UV to T, mark V as visited, and append V to Q. So these are the main three steps that we are going to perform each time we find that the current vertex U has an unvisited neighbor V. So the algorithm is quite easy. The initialization step is just marks all the vertices as unvisited except the root, which is marked as visited, and then in the main loop the algorithm keep on visiting vertices from the current vertex as long as the Q is not empty, right? So before we take an example, let us see how fast this algorithm is, or in other words, let us compute what is the time complexity of this algorithm. So the initialization step just takes n steps, right? If n is the number of vertices in the graph, so that means the initialization just runs n times. The next while loop runs as long Q is non-empty, right? So under the while loop, what happens? There is a for each loop, and which runs just du times where U is the current vertex. Du is the degree of the vertex U, and you must know that then we just sum all the vertex degrees. What we get? We get the twice the number of edges, 2m, twice the number of edges in the graph. So the total time taken by the while loop is sum of all the vertex degrees, and which is actually twice the number of edges, 2m. So now what is the time complexity? We have just seen that the initialization step runs n times, so n plus 2m. So time complexity is big O of n plus 2m, but 2 is a constant, so we can just remove it. So it actually just can be written as big O of n plus m. I hope you are familiar with the big O notation. Here n plus m, if you just compare these two numbers, you will see that in practice m is much larger than n. So time complexity is essentially m, OM. So what does it mean? It means that the algorithm takes time just proportional to the number of edges in the input graph. So it is the fastest one of the fastest algorithm for graph traversal. In fact, linear time algorithms are the fastest algorithm for graphs, and in general algorithms are quite takes a lot of time, because they could be of polynomial time complexity. The time complexity could be of order of say n square, n cube, or just some power of both n and m. So this is one of the fastest algorithms, and that's why this algorithm is quite frequently used. It is now let us see how to actually illustrate this algorithm using an example. So we are given here a graph. You can see here the graph has 8 vertices. Let's start with the vertex v1. So v1 is here the root vertex, as we need a root vertex and apart from the input graph. And what else is given? We are given two containers, Q and T. So initially V is marked as visited, so we shall use the color red to mark the vertex as visited, and black color automatically means that they are unvisited. So V is marked as visited here. So V is appended to Q, and T is initially empty. So the tree has no edges right now, it is just an empty set. So now to traverse from V1, how do we traverse? We just have to visit each neighbor of V1. So the neighbors of V1 are V2, V7 and V8, right? There are three neighbors. We shall visit them one by one, say in the order, first V2 and then V7 and then V8. So in this order, suppose we visit V2, then what happens? V1 has been removed from Q and V2 has been inserted, right? And what else? We have just added the edge V1, V2 into the tree T. So this is the first edge that we have found for the spanning tree. Next, V2 has been visited, so we visit the next vertex, that is the next neighbor of V1, which is V7. So after visiting V7, so V7 is also inserted into Q, and the corresponding edge V1, V7 is added to T. Next, we visit V8. So again, V8 is added to Q and V1, V8 is added to T. So thus far we have got 3 edges in the spanning tree, which are V1, V2, V1, V7 and V1, V8. And Q contains 3 vertices, V2, V7 and V8. You can see that Q contains the vertices in the order they are visited, because we visited V2 first and then V7 and V8. So in that order they are coming. And we have to remove vertices from the front side. that is from the left hand side from here. So V2 next, since V1 has all the neighbors of V1 has already been visited, we just move to the vertex V2 in the queue. We just remove it and we shall start visiting the neighbors of V2. So as you can see, there is only one neighbor which is not visited of V2, which is V3. So we just visit V3. So in this case, V2 has been removed from the queue and V3 has been inserted at the end, and the age V2, V3 has also been added to tree. Okay, now V2, all the neighbors of V2 has been visited. So we just move to the next vertex in the queue, which is V7. So we remove V7 and shall visit all the neighbors of V7. So now we see that so the only unvisited neighbor of V7 is V6, right? So that V6 is visited, it is just inserted in the queue, and V7 is removed, right, as the change you can see here. So and the age V6, V7 is also added to the tree. So thus far the tree has 5 ages: V1, V2, V1, V7, V1, V8, V2, V3 and V6, V7. And Q is still non-empty, so we have to continue the process. So now the next vertex that has to be removed from Q is V8. But as you can see in the graph, all the neighbors of V8 has already been visited. So we just remove V8 from Q, but there is no change in T because no new age is being added. So V8 is just removed from Q, but there is no change in T. Again we can see that Q is still non-empty, so we just remove the vertex V3 from Q. So let's see what are the neighbors which are still unvisited in this graph. So we can see that the two neighbors V4 and V5 are still unvisited. So we just visit them one by one. So first we visit say V4, then V4 is marked as red. So V3 is already removed, okay, and V4 has been inserted in the queue, and the age V3, V4 has been added to T. Okay, and next we visit V5. So V5 is added to Q, and the age V3, V5 is also added to T. So now you can see that although we have visited all the vertices, but Q is still non-empty, so the process has to be continued. Let's see what happens. So the next vertex that we are going to remove from Q is V6. So we just remove V6, but all the neighbors of V6 has been visited, so no change is going to take place in T. Similarly, we just remove V4 because all the neighbors have been visited of, so there is no change in T again, and likewise for V5. So at the end we get that Q becomes empty and the process or the algorithm stops here. So the spanning tree that we have constructed has ages V1, V2, V1, V7, V1, V8, V2, V3, V6, V7, V3, V4 and V3, V5. So this is the spanning tree. So you can just verify it whether it is a spanning tree or not actually. So the graph has 8 vertices, and any tree or any spanning tree must have exactly 7 edges, right? Because a tree on n vertices has n minus 1 edges. This is a fundamental property of trees. Here you can see that the tree has exactly 7 edges, but apart from this, what else we need to verify a tree is a connected graph, right? So you can see that in the graph, the tree is the tree that we have got is actually connected. Why we always get a connected graph? This is something that one can easily prove. This just forms a part of correctness of algorithms. Although in this session we are not going to just prove whether this algorithm works right or not. This is just a fundamental question and can be checked easily. So here we have seen that what the BFS algorithm is, how it works, and we have just looked at one example, right? So the idea is very simple. We have, let's look back the general framework of the BFS algorithm before we come to some other applications. So we just quickly go back to the algorithm. So the general framework is that it just contains one initialization step and one main loop. So in the initialization step, we just do some initializations like marking all the vertices as visited or unvisited, and just setting the sets with some empty value or some initial values, right? The process starts in the main loop, and in the main loop we just check while the queue is non-empty, we perform certain steps. The first step that we perform is we just pick a vertex u from the queue, and that vertex is the first vertex, right? We always remove the first vertex, and then from that vertex we start exploring the vertices that are adjacent to the current vertex, right? That is to u. So while exploring, we just check if the current if the current vertex has any neighbor which is visited, then we can do some steps. Here we have just only excluded such steps, but if it is unvisited, then we just mark that neighbor visited and just append it to queue. And here the age is also appended to the tree. So these three steps can be replaced by some other appropriate steps depending on the application which we are interested in. So we have to only keep in mind what the general framework is, which is just while the queue is not empty, we just pick the first vertex, say u from the queue, and then for each neighbor v of u, we shall perform certain steps. That's what the general framework is. Now with this framework, we move ahead. So the first application that we are going to see of this algorithm is in finding the components of a graph. So as you can recall, a component of a graph is a maximal connected subgraph of it. Maximal connected subgraph means a subgraph which is connected and which is not contained in any connected subgraph larger than it, right? So one of the very first thing that we do while finding the components of a graph is we need to just select a root vertex, and then from that vertex we explore all the vertices which are reachable from that vertex, right? So if suppose your root vertex is R, then we just explore all the vertices reachable from R. Now reachable means there is a path, of course, there is a path from root to the every other vertex. So because of the definition of component, we will always find, no matter what route you choose, you will always find the same component. So this is one of the very uniqueness about BFS component algorithm that we are going to discuss. you know, no matter what route you choose, you will always land up with the same component because of the definition of component, because it is a maximal connected graph. So if you just pick one vertex, you can simply extend it by including all its neighbors, and then neighbors, and so on, as long as you can reach right from the root vertex to the other vertices. Okay, so let's look at now this algorithm, what actually it does. So it just takes the input graph G and the root vertex R. So in the input graph, the graph could be connected or disconnected, right? That we do not put any condition. The result is that it just gives us the component of G that contains the root vertex R. So again, here you can see that there are certain initialization steps. Here C just initially contains the root vertex, that is the beginning vertex from where the search starts, and Q also contains R, and then the root R is marked as visited. Okay, so okay, everything else is still unvisited. Now the main loop is, while Q is non-empty, we just pick the first vertex, say U from Q, and then for each neighbor V of U, what we do, if V is unvisited, then we append V to C and to Q, right, and mark V as visited. So here we can see that we have picked a vertex U, which is the first vertex from Q, and just explore all the neighbors of U, and whenever we find that some neighbor is unvisited, that neighbor is appended to C and to Q, right, and finally it is marked as visited. So this way the component C keeps on growing, right? It just, so when the algorithm stops when the Q becomes empty, that means there are no longer vertices that need to be visited, right, in the component, in the current component. That means when Q becomes empty means that all the vertices which are reachable from R have been visited. So let's look at now this is just one component finding algorithm, but we need to write a small code for finding all the components, right? So now what is the general strategy? Once you have found one component, you would simply just display it or print it and remove from the graph, and just pick another root vertex from the remaining vertices, remaining unvisited vertices, and just repeat the same process from that root vertex. So in that way you will also find another component, and that component can be printed, and if there are still unvisited vertices, you can again call this. So you have to repeatedly call BFS algorithm each time with a different route to print all the components of the graph. So the code or the algorithm for finding all the components is just simple as given here. So it just takes input graph G, and its output is all the components of G. So initially we mark all the vertices as unvisited, and while G has unvisited vertices, what we do, we just pick an unvisited vertex, say R from G, and then call BFS component with root R. So this way we shall continue to print components as long as there are unvisited vertices. So we just pick one root, print one component. If there is some unvisited vertex left, then we pick one of the vertices at the root vertex and then print another component that contains this new root vertex, and keep on printing it as long as there are unvisited vertices. So this is one of the applications that we have discussed of the BFS algorithm. So what we have done, actually we have not done much change in the algorithm. We have kept the general framework intact. Only thing that we have changed here is, let's go back to the BFS component algorithm. So in the general framework we have just what changed, only the last time we just said that there are 3 steps that we performed while constructing a spanning tree. Also there were some different container, right? There we are using the container T to store the edges, but here we are not storing the edges, instead we are storing the vertices. Okay, so the change that we have done in this algorithm is that in the 3 steps that we needed, one step is clear, the same thing, mark V as visited. There also we were marking vertices as visited as soon as they are found unvisited, and V is added to Q. This is all. Yes, so we can just have a short break and then continue.
Do you wish to be part of a television studio like this, or any other media system, or already part of any media system, want to enhance a new set of skills? Welcome to School of Journalism and New Media Studies. Here in the School of Journalism and New Media Studies, we are offering program for all set of people to learn and enhance their media skills. The vision of School of Journalism and New Media Studies is to generate a new set of professionals in the area of media and communication studies with understanding about the role of media in the national development and global understanding. We offer innovative programs in the field of journalism and mass communication that sets the benchmark of high quality learning and teaching process at the national level. We offer these programs across the country with the help of our regional network as well as study center. Same manner, many of our programs are offered through online mode with a sophisticated learning management system. SOGNMS offers programs from PhD in journalism and mass communication till certificate level. We have masters in journalism and mass communication. The eligibility is bachelor's degree, and we are introducing this program in 3 languages: Hindi, Tamil, and distance mode. We have 4 postgraduate diploma programs, specialized areas in the field of development communication, digital media, electronic media, and journalism and mass communication program. And all these 4 programs are available in distance mode. 2 programs are available in online mode, development communication and digital media. And we have specialized certificate program in community radio. IGNOU employs various media and communication tools for better teaching and learning process. School of Journalism and New Media Studies utilizes this media system for delivering all our programs. Come and join with us for exploring a new career and enhance your media skills.
Okay, welcome learners. So we were discussing about the BFS algorithm and some applications. So right now we are at the algorithm BFS component. So what we have said is that while looking at the BFS algorithm, we just have to change only certain steps in the algorithm to get some other algorithms, likewise BFS component. So in this algorithm, what we have seen is that the container Q and mark is visited, and while Q is non-empty, we just keep on picking up vertices from Q from the front side, and then explore their neighbors in a sequential way. And while if we find that any neighbor is unvisited, mark it visited. So this process continues until we find that Q becomes empty. So let's now look at an example how this algorithm works. So here we are given a graph which has two components. So we again pick the vertex V1 here as the root vertex. So V1 has three neighbors V2, V7 and V8. We can just traverse them in any order. So suppose we traverse them in the order V2, V7 and V8. So first we visit V2, then V2 is added to C and also to Q. Now note that V1 has been removed from Q. Okay, next we visit V7. So V7 is added to Q as well as to the component C. Again we visit the next vertex V8, which is headed to Q as well as to C. Move to the next vertex in the Q, which is V2. So we start the process of exploring vertices from V2. We can see that only one neighbor of V2 is unvisited, which is V3, right? So now V2 is removed from Q and V3 is inserted, right? And V3 is also inserted in the component C. Now we can see that although all the vertices have been visited, but Q is still non-empty. So we have to run the process as long Q is non-empty. So we just pick the vertex V7, but V7 has already been included in C, so there is no change in C. Then again we just remove V8. Again V8 is already there. V3 is already there. So we see that now Q becomes empty, and the current component contains the vertices V1, V2, V7, V8 and V3. So we can just print this component, but we can see that there are still vertices which are unvisited. So we have to pick another root vertex to find another component. So for instance, we choose the vertex V4. So V4 is in Q and as well as in the new component C. So we visit the vertices V5 and V6 as they are the only two unvisited neighbors of V4. So V5 is added to Q and to C, and then V6 is added to Q as well as to C. Now all the neighbors of V4 have been visited, right? So we move to the next vertex, which is V5. So V5 is removed, but there is no change in C because it has already been there. Then V6 is removed, and finally we just print the component which contains the three vertices V4, V5 and V6. So this is how the component finding algorithm works. So thus far we have seen one application. The next application is in finding or checking whether a given graph is bipartite or not. So before we come to that application, let me just tell you what are the things or facts that you need to know about bipartite graphs. So just recall that a graph is bipartite if its part is that there is an edge from that means every edge has one endpoint in the one part set and other endpoint in the other set. In other words, you can say that graph is bipartite if its vertex set can be partitioned into two non-empty independent sets, right? So now there are some other facts that you must know about bipartite graphs, and which are like a graph is bipartite if and only if all its components are bipartite, right? And more importantly, a graph is bipartite if and only if it has no odd cycles. So what are odd cycles? Odd cycles are just actually means, look at the second statement, a graph is bipartite if and only if it has no odd cycles. It says that if the graph is bipartite, then either it has no cycles, or if it has any cycle, then that cycle must be of even length. It must be an even cycle, right? In other ways, you can just go in the reverse direction. It says that if you check that all the cycles of a graph are either, if the graph either has no cycle or if all the cycles are of even length, then that graph is bipartite. So manually it is quite difficult to check each and every cycle and check its compute its length. We shall see an algorithm that does this task quite fast. Just a variation of BFS algorithm. Now, what actually, before coming to the algorithm, let us see how the odd cycles are found. So, another statement is that every odd closed walk contains an odd cycle. So, now what is an odd closed walk? An odd closed walk is a closed walk of odd length, right? So, if you are given an odd closed walk, then you can certainly say that there is an odd cycle in that walk. So what we essentially need to find in a graph is that whether it contains an odd closed walk or not, to just prove that it is not bipartite. So let's look at some hypothetical situation when one can find an odd closed walk. So suppose you are given some vertex R and two adjacent vertices U and V. So just compute the distances of U and V from R, and if it happens that both the distance of U and V from R are say of the same parity, that is either both are odd or both are even, then what happens? Then the walk from R to V and V to U and U to R, that is the closed walk containing these three vertices, it would be a walk of odd length, right? Because the distances of U and V from R are odd, so their sum becomes even, and plus one edge UV, right? So this gives us an odd closed walk, and by the fact that we have just seen, every odd closed walk contains an odd cycle. So whenever we find such a situation, we can easily say that the graph is not bipartite. So in the algorithm that we are going to see, we have to only just at each step just check whether the graph has any odd cycle, odd closed walk or not. In essentially, we are just checking whether from the root vertex is there any pair of adjacent vertices U and V which are at distances having at the same parity. Okay, so we now come to the algorithm. The algorithm is given here. So in the initialization step, we just first compute, we just set the distance of R from R as 0, and the set Q contains initially R, and R is marked as visited, right? And then the main loop starts. While Q is non-empty, we just pick the first vertex, say U from Q, and then for each V belongs to NGU, we just check whether V is already visited or not. If it is already visited, then we just know that the distance dRV, I mean the distance of V from R, has already been computed, right? In that case, we can see whether dRU and dRV are of the same parity or not. If they are, then we just return false. False here indicates that the graph is not bipartite. So as soon as we find any pair UV of adjacent vertices whose distances from the root vertex are of the same parity, we just immediately return with the false condition of the false statement, right? That means the graph is not bipartite. But now there is another statement in this also. So what happens if V is not already visited, right? In that case, we have to compute the distance of V from the root vertex, and which is just one more than the distance of U from the root vertex. That is dRV equals to dRU plus 1, right? And then we just append V to Q and mark V as visited. So these are two things that we need to check each time we find a neighbor V of the current vertex U. If it is already visited, we just check the parity of the distance dRU and dRV, and if the parities are of the same, we just immediately say that the graph is not bipartite. Otherwise, if the vertex is not visited, and we just compute the distance of this vertex from the root vertex and append it to Q and mark as visited. Okay, what happens finally? Finally, you can see that there is a return statement which is written as return true. So this statement only works when the all the cycles have been checked and they have found to be of even length, right? That means there is no pair of adjacent vertices which are at the distances of the same parity from the root vertex. So in that case, the graph becomes a bipartite graph. So let's look at an example. So we are given here a graph. So we just choose again here the first vertex, the root vertex as V1. So we have just marked in parentheses the distance of V1 from V1, which is 0, right? So there are two neighbors of V1, that is V2 and V6. So we visit them one by one, and also since they are unvisited, so we just compute their distances and mark them visited. So their distances are 1 from V1, right? Okay, now from V2 we just visit the three neighbors of it, which are V3, V7 and V8 in this order. Okay, so their distances are marked as 2 because V2 has already V6, right? So from V6 we visit V5. Okay, so V6 has distance 1, so V5 has distance 2. And now following the order, we just visit the vertex V4 from V3. So its distance is computed V7. Now from V7 we can see that the vertex V5 is already visited, right? And what else you can see here? The distances of V5 and V7 both are 2 from the root vertex. That means they are both the cycle is just to in case you find that you do not have any odd cycle, then the graph would be bipartite. So this is how we can use the bipartite checking algorithm. So that is one thing that we seen. The BFS algorithm is one of the fundamental algorithms as we described in the beginning, and we have only picked two specific applications, but it has numerous applications and in many contexts and outside graph theory. Because why? Because it is one of the fastest algorithm. It has linear time complexity, and moreover it is very simple to understand, which is very easy to understand. So let's summarize what we have discussed in this session. We described the BFS algorithm in detail, and we just picked up two specific application of this algorithm, namely finding the components of a graph and checking whether a graph is bipartite or not. So in all these applications, what we have seen that the basic or the general framework of BFS algorithm remains the same. What we have changed is only the statements inside the commands that we have. So that could be changed depending on the application or the type of problem. So that is all in this session. If you have any query, you can ask.
Are you a fresh graduate? Do you want to fulfill your educational aspiration by pursuing higher education in various interdisciplinary and multidisciplinary areas like environmental science, environment and occupational health, philosophy, sustainability science, folklore and culture studies? If yes, the School of Interdisciplinary and Transdisciplinary Studies offers various programs like Master's Program, Graduate Program, Postgraduate Diploma, Certificate and Appreciation Program. The school offers 5 Master's Programs. Master of Science, Environmental Science. The eligibility criteria for MSc Environmental Science is Graduate in Science, B.Tech, BE, Agriculture Graduate, Forestry Graduate and Veterinary Graduate. School also offers